Linear prediction for to find a set of weights in the array processing. So once again, you collect data at a set of sensors, and you want to put a set of weights to combine them into an output. So this is Wi xi of t. So in linear prediction, if you recall, the outputs x1, x2, etc., xn are used to estimate the next output. So let me assume here, this is in general, let me assume that this is unknown, and we are going to estimate the unknown, the last one, in terms of the previous ones, AI. So here I used Wi in linear prediction because I need to bring, it's desirable to bring, as you are going to see, everything to one side. I am going to use minus AI, so Wi. So I'm going to use this approach to figure out the weights. So here, of course, xm minus xm bar becomes the error. So this is, now I can write, using this notation, I can write this as xn minus I equal to 0 through m minus 1, right?
Professor, what is n? What is n?
N is like a time running index, right? Yeah, hold on. So then we could make it I equal to 1 through n, right? So this will be like xm. So according to this notation, I equal to 1 and 2. So this will be, let's say, xn. Then this will be xn minus 1 hat, right? xn. I'm going to estimate the xn in terms of the previous ones.
In the graph, are you writing the xn or xn?
Yeah, I mean, we'll come to the graph later, but I'm saying this is the linear prediction idea, right? Look at here, I equal to 1 through m. So you're using the previous m minus 1 outputs. I mean, quantities to estimate the current, the xn, the next value.
The index on the summation should be n as well.
N, right? Yeah. Index on the sum. No.
No, 1 through m you have, but it should be n.
1 through m, right? And let's say m previous values.
Oh, okay, gotcha.
N is like the running index, right?
Then why is yt equal to sigma I?
Yeah, as I said, I'll connect this with this problem, right? Yeah. But you can see I'm trying to estimate this output, assuming that these are sort of, this goes forever. I'm trying to estimate one output in terms of the previous m outputs, right? 1 through m minus 1 outputs. You could, I mean, we don't have to go to that far, but I'm saying, think of that scheme where these are this is the running variable n, and then we will consider this specific case pretty soon. So this is the general case as we did few days back, right? The general case in estimation, right? So When I equal to, so it shouldn't be from I equal to 0 through m minus 1 then? Yes?
Well, A0 then should be 1.
Yeah. Yeah, because when I equal to 0, you get xn, right? With A0 equal to 1, right? That's good. Then you know how it goes. You want to minimize the error, right? Minimize the mean squared error. And the minimization is with respect to this A case. When you take the derivative with respect to A case, you get the condition that error is orthogonal to data, right? Data, I'm going to write it as n minus k. So if I use error is orthogonal to data, so error is going to be ai x n minus I x n minus k, and the expectation is here, this should be 0. And k is so this now reads summation ai T1 minus T2, right? So the data points is K, 1, 2, 3 in the past m minus 1 samples, right? And you have one more equation. If I call sigma squared to be expected value of error, absolute value squared. But so this you can, error is orthogonal to data, so you can write this as sigma ai x n minus I. But this error is orthogonal to all the data points except xn. So this will turn out to be simply epsilon xn star, right? And now if I substitute for epsilon n, this comes ai xn minus I xn star, right? Expected value here. But this is T1 minus T2 is simply sigma ai r minus I, which is ri star. So let me put down these equations. So the first m equations, m minus 1 equations are 0, and the last one, except I'm going to get my things in order. So I'm going to write this equations, but I'm going to start from this here, see whether. So I'm going to a minus 1, so I equal to m minus 1, but I'm also going to start from this end. So I'm going to take the m minus 1 equation. So I hope if you put it up, you will be able to see what I'm writing. So convince yourself this is true. So I put k equal to, I took the last equation and I am coming from this end to get this in order. So then this will be R1 star, R0, R1. All right, so from here we know how to solve for each one of these. Some of this I already went through this. If you want the first unknown, look at here, Kramer's rule, you bring this row onto the first, bring that column into the first column, and the determinant of that divided by the determinant of this. Determinant of this is delta Tm minus T. This is a Toeplitz matrix. Its determinant I am going to denote it by delta n. Okay, so delta n is the determinant of Tn. So this will be, the determinant of that will be, so if similarly, if the last entry, look at here, the last entry, this unknown is going to be, the determinant, the denominator determinant is m minus 1. And the numerator is going to be, I replace the last column with this column. So this is going to be R0, R1 up to Rm minus 2. Then you have 0, 0, etc., 0 sigma squared. And here, so the last, so now you can expand this determinant by the last column, but there is only one unknown. So that's sigma squared multiplied by this. So this is going to be sigma squared multiplied by delta m minus 2 over delta m minus 1. So from here, we get sigma squared is delta m minus 1 over delta m minus 2. This, so that's the minimum mean squared error. We need that. So now let me solve for this unknown. So that unknown m minus 1, etc., a1, 1 is going to be sigma squared. That's a constant, right? Then Tm minus 1 inverse. Then you have this. I pull the sigma squared outside, which is fine, right? Because everything else is 0, I can write it that way. Now we'll use this identity. ABCD, if you want, you can expand this as so if I put the D equal to 0, this is a useful identity. Especially if C is one row, then you don't need a determinant here. If this is M 1 by M, then you don't need a determinant. And if I bring this minus 1 here, so this is the identity I want to use there. So look here, I have so let me form this vector h of c, this polynomial, which is sigma ak zk. So I can write this as cm minus 1. But I already solved for this here. So I'm going to put it here. So these are all methods, sigma squared. Then you have zm minus 1, etc., z1. Then you have tm minus 1 inverse. Then you have 0, 0, 0, 1. Look here, I am this form. So this is now, A is what? A is the Tm minus, so this is 1 minus 1 over delta m minus 1. Then you have this matrix, Zm, Zm minus 1, etc., Z1, 0. Where is B? Yeah, this 0 here. And this is 0, 0, etc., 1. Remember, I put C here, B here, and then you need Here, where is this? So C, A inverse, so you need A here, right? A goes here. So A is going to be Tm minus 1, right? Tm minus 1 starts R0, R1, etc., Rm minus 1. So the row here is Rm minus 1 star, etc., R1, R0. Before that, Rm minus 2 star, etc., R0, R1. Okay. Now what? Now, because of the 0, I can again expand this determinant if you want along the last column. Look at here, everywhere 0 except this. And because this is one place above this, when you expand it, it will be minus 1, minus goes away. So the expansion will be what? Get rid of this row and this column, the remaining stuff. And there is a sigma squared, right? I forgot the sigma squared is a scalar here. So let me substitute for sigma squared. Look at here. Delta m over delta m minus 1. So this will become this, right? Now what? Finally, I'm going to do this simple substitution. So this will turn out to be, and I'm going to use this polynomial. And you can see that's a polynomial, right? Because you can. So now this is going to be R0, R1, etc., or m minus 1, then R1, R0, etc., Rm minus 2. But the last row is so I got rid of that 0 and all that. So this is going to be R0, R1, right? This will be R1 here, R0, R1 star, etc. So why is this polynomial useful, right? So if you somewhere here, what is it? Any questions? So look here. The epsilon equal to this convolution on a running index of n. So if you take the Z transform, remember this is a convolution here, right? Discrete time. So if you take the Z transform of this, it's the Z transform of this, but this is only a finite dimensional filter. So that's going to be this filter. AK, ZK, this one. Now I have given you an expression here, compact expression for this. That's it. That's why this polynomial is important. So multiplied by x of z, consequently, so anybody, what is the output spectrum? So look here, the output spectrum is the, so this is your input, right? This is your filter, this is your output. Output spectrum is sigma squared because this is, we saw it's a white noise, right? So this is so constant equal to this transfer function squared multiplied by this. So I hope you see that this is so again this sigma squared is coming up. So I am going to substitute for the sigma squared. So look here again. So this you can write this as in this manner, right? I took the square outside. And sigma is here, right? Sigma is here. Sigma is square root of delta m minus 1 over delta m minus 2. So I'm going to, so I can write like this, right? Previously sigma was here, so I'm going to, so rather than write another line, let me put it here. So 1 over sigma is going to be delta m minus 2 over delta m minus 1. Right? So you see that delta m minus 2 will cancel with this. So this whole thing will turn out to be So what's the moral of the story? We will use this as the linear prediction filter, linear prediction estimator. So how does it work here? So remember, this is your steering vector coming in here. So if you, of course, you can expand this into a polynomial, because after all, what is happening here is, this is of the form of 1 over some polynomial square, right? We found out these weights through, except this is a compact expression. Right? So you compute, these are from the covariance matrices, you compute all these covariances. You can expand this if you want and write it into a polynomial form, and then you find the then you find the spectrum. So you have a third technique now. So this R case would be in our case, it would be the covariances between these different sensors. So what I'm going to do next, which is a very interesting thing, I'm going to, as complicated as it is, I'm going to compare this with the previous method and see which one has a better resolution, right? So if you remember, so let me do that next.